Hello, everybody.
Hi.
Hi, Patricia.
Good morning. I think we can wait for 3 more minutes and then we can get started. Okay, I think we can get started now. Um so last time we were talking about the AI paper, and I think we had a very good discussion. So I think Anurag, I think you are unmuted. Um, yeah,
I got
thank you.
scared. I got scared for somebody's safety there.
Yeah. Um, um, Actually, I don't think I've seen you before, Anurag, in the meetings. So if at some point during the meeting you want to introduce yourself, that would be nice.
Sure. Give me a few more minutes.
Okay. Okay. Yeah, let us know when you're ready, and then um, yeah. So in the meantime, yeah, so I was saying we were discussing the AI white paper. And so I think what we can do, there were a lot of interesting thoughts that came up from that discussion. So what I think we can do with that is I'll make a list of all the things that were brought up. And then during the following meetings, we can, put them as action items, and assign those action items to to members of the work stream, so we can start solving those I guess questions and concerns, if that makes sense with everyone. But then I guess for now, let's continue discussing the AI white paper. Sorry, this is not what I want. I'm going to stop sharing. What is it that I want? Yeah, so we can continue discussing the AI paper if I, yeah, desktop too. Do you guys see my the paper, or
Yeah, we
um,
see
you
PDF
see the
overleaf, I
paper?
guess. Yeah.
Okay, cool. Yeah, last time I was sharing another thing, so hopefully this time doesn't happen. Okay, so yeah, so I think we didn't get past this is the third page of the AI white paper. So and we were talking about about the benchmarks that we have used for our characterization. And there were certain concerns about the benchmark. So I'll write those down and we can start assigning people to concerns so we can address those. But then to move on in the conversation, we'll take it back next time. So we kind of did the profiling, so we could have how much scratchpad do we need, how much for input feature map and for parameters. And then we started to talk about which chiplets we would need in order to build this modular architecture. So we start with an interposer. So the first thing we do is to propose this grid, this two-dimensional grid of chiplets. And in this case, the chiplets are completely generic. So I guess you can put anything you want in there because the chiplets are connected through a network on chip. And this network on chip, or I guess network in package, yeah, where that would enable the communication from any place in the grid to any other place in the grid. And then, so we will have to define or yeah, how does this networking package would look like to enable the fast communication between the dies. Then of course we have one IO chiplet that would enable the chip-to-chip communication. So, and then we would need some sort of memory controller or memory chiplet that would enable the access of these generic chiplets um, to some sort of DRAM, to any DRAM technology that we chose. There is the option to put DRAM on chip, but let's discuss that later and what are the limitations of putting this DRAM on chip. Okay, so that's kind of the general high level for the interposer. And please feel free to stop at any point if you have some questions or concerns to add here. But the idea of the interposer is that if we have an interposer, we could reuse these across different designs because so that's something that we could also try to reuse depending on the system. Then we also have the AI chiplet, and this AI chiplet is what is defined by the characterization that we did for these benchmarks. So we find that, so we do run synthesis and place and route for different AI chiplets. So we find these Intel 22 nanometers from the Gemini publication. So we just put that in there from that publication. But we also run synthesis for sub 20 nanometers, sub 10 nanometers, and sub 5 nanometers. And the reason why we're not saying the specific node that we're using is just to break any confidentiality rule. But yeah, so and this was done by various members of the work stream. So they took the RTL that we had for an AI accelerator and then got this number. So we know the area that would take to have these different AI accelerators for different sizes. So you can have, we talked last time what this AI accelerator look like, and it's basically a systolic array. There is another one that is the one used by NVIDIA, but in this case, we are focusing on the systolic array. And the systolic array can vary in size, so we can go from 16 by 16 to 512 to by 500 to 12. And then we have those numbers, and basically these area numbers these synthesis results will define the area of each chiplet. So that's for the AI chiplet. So then we also have, we want to understand, there is this trade-off between the data lanes available versus the area of the chiplet. And this will let us define the bandwidth of each of the AI chiplets. I think, George, you have your hand up.
I do. Oh, I'm sorry. I was going. Okay. Nope. My bad. I wouldn't want to
Okay.
click something different.
Okay, cool. Yeah, so, and then with this, so basically we take the available data lanes, we map the bandwidth that we would need for different sizes of the AI chiplet, and with that we can define the die-to-die interface. So that's something that so we talk about the chiplet bandwidth, and then we define the die-to-die interface. What would it take for it? So what we find is that if we use interposers with a bump pitch that is between 40 and 100, we definitely need to go with UCIe or a bunch of wires. But if we have an advanced interposer that could give 20 micrometers bump pitch, we could have a fully parallel die-to-die connectivity. And this is where we can advocate for, okay, what would happen if we have an ideal scenario. But if we have something below 40 to 100, then we need to study what happens with UCI and bunch of wires. We do something similar to a memory chiplet, where we take some parameters that we get from the technologies, and then we get this table where we have, okay, so if we have a sub 20 nanometers or a sub 10 nanometers, what area would we need? Like if we have a 5 by 5 or 3 by 3 millimeters chiplet, how much area, how much memory can we fit on that? Yeah, so for example, if we have the sub 10 nanometers and we have a 5 by 5 millimeters chip, we could fit 34 megabytes of memory. We don't have data for like, let's say, a sub 5 nanometers technology, but if anyone in the workstream could share that data, maybe we can finish this here and get this data for memory as well. So with this, we have this chiplets library for AI. So we have the systolic array, of course, that is the AI chiplet. We have the scratchpad chiplet. We have a vector unit chiplet, and this vector unit doesn't become relevant until we start to look into AI. We can talk about it a little bit more, but basically what we find is that embeddings are really inefficient if we try to run them in these systolic arrays, and that's with this vector, when these vector units come into place. But we don't have data for that, so we don't have any synthesis results, or we just know we know for sure that we need a chiplet for that. And then we have a chiplet for nonlinear functions and accumulation. And there is a debate there whether if this accumulation unit with nonlinear function could be a separate chiplet, or it could be embedded, it could be part of the AI chiplet. So I don't know if anyone has some opinion about that. But yeah, so let me know if you have some opinion about that. But yeah, so that there is some discussion there, or whether we do need a separate chiplet, or we need or we can unify it with the AI chiplet. Part of the reason why this could be a separate chiplet is because this accumulation unit require memory. So it still could take a large amount of area. So, but this is something that we could discuss as part of the work stream. If
Are there any use cases? Hi, Patricia, this is Arvin. Are there
Hey,
any use
Arvin.
cases where sitting in isolation, this chiplet would be otherwise useful? Or is it only useful when it's combined with the AI chiplet?
Yeah, I think that's a good question. The what I would say is that, and I don't know if this is something that could be useful for everyone. That's something that we will have to discuss. But um, what this would allow us is to maybe give some flexibility on the activation functions that we could use. So if certain applications would benefit from YELU and would never use ReLU versus other could use different activation functions, then this could help us do with the modularity part where we could choose what the accumulation unit would work depending on the application we're targeting. That's one case where I would say, okay, that could be a benefit. And the other benefit I would think of is the fact that, um, um, we like this chiplet is pure processing. It has very minimum amount of memory on it, other than maybe some buffers, while the accumulation unit could share some of the required memory for other functions as well. So this accumulation unit could be something shared between some part of memory that needs to be very close to the accumulation units and the accumulation and nonlinear functions. But I don't know if anyone else have some take on it.
Well, if we do add that, some of the HPC applications do accumulation like a stencil operator I was looking at. Um, the heat equation, for example, you can simplify it such that it's basically an addition between points. So we could reuse that unit.
Also, accumulation is the biggest source of error. And so you could have the accumulation unit operate at a higher precision than the operands that it's working on.
I agree with that statement, but I think maybe the question to me is, would you ever be doing an accumulation that doesn't really pair with the AI chiplet? So, I mean, would it be useful to have a different processing unit that fed into the accumulator? So you'd really like to have these kind of more modular? Or is every application that we can think of for this particular accumulator really tied to the AI chiplet?
I think that's what George, correct me if I'm wrong from what you said, and you can maybe speak up, but I think that's the point that you're trying to make, right, George? So this accumulation chiplet, if we make it into a chiplet, we can take it and use it for an HPC application such as a stencil operation, where we have an accelerator that is not AI, is a stencil, and that one fits the accumulation unit. Is that right?
Exactly, yeah. And we can make a similar argument with the vector unit, by the way, but for different applications. Haven't looked into those yet, but yeah, that's exactly right. We can, yeah.
So I guess, Arvin, I guess the answer would be the accumulation unit. If we only think about the AI application, maybe it doesn't make a lot of sense to separate them. But if we think about the modularity argument, where we can use this accumulation unit for other applications, for a completely different benchmark paired with a completely different set of chiplets, then there is some value there.
Mhm.
That makes sense.
Yeah, I think that's the direction I was trying to push this. So yeah, that's great. Thank you.
Okay, so I think I took notes of that. So I don't know if, yeah, so I took notes of that, and then we can add it into this paper and into the following one. Okay, so cool. So the die-to-die protocol and network in package. So I'm trying to think. Okay, so yes, so basically, so now we have a network in package that would enable any chiplet in any place on the grid to communicate. So we need to describe a packet structure, I think, and we don't have to go into details, but it would be nice that we can talk about how this would look like, and this is something that hopefully someone else can take on, And what I was looking into other OCPs work streams, and there is, I don't know if you guys, if someone here have seen that presentation, but there is one work stream that is defining a packet for UCIe. Is that right?
I'm not sure. Maybe. But I was gonna say if nobody else wants it or I can work with somebody, I'm interested in this part.
Okay, so
What do you mean? Sorry, what do you mean exactly by packet? Because within the UCI, even the streaming specs, there are FLIT formats. I don't know if that's the same thing or is this something a little different?
I think yes. So I think what like we don't have. I don't think that we need to define anything new. I think what we have to do is investigate how this, you know.
So Luis, this is Anurag.
Yeah.
I'm in a safe place now in office.
Okay, nice. I'm glad to hear that.
No, sorry, but I thought I was on mute, but some random guy started honking in the back. Mm, but yeah, like the way you are describing this packet interfaces, UCIe has its own streaming interface, which is basically raw bytes going in. UCIe also supports PCI or CXL over UCIe, so you can have a PCI like packets or UCXL like packets going over the UCIe, so you could have that opportunity. Or you can simply have XI packets just pass through UCIe streaming interface. So all that is possible, and I would love to interact with you and see what means. I haven't read the paper. I'm sorry, so I don't want to speak much on it, but we can discuss offline maybe, or you can, or somebody send me the link to this work, and I can at least upgrade myself.
Yeah, I think
Happy to work with you guys.
that would be great, Anurag. So what I would suggest then, so since George and you has also expressed interest on this, I think we can get together. And then I'll send you the draft. It's a very drafty paper, so I apologize for that. But that gives an idea of what we are going after. And yeah, so and then George and Anurag can get together and try to define this. But yeah, so the idea is that we don't need to say anything new. We just need to make sure that the interface that we have here between the chiplets um, and the information that we are going to send is some sort of something that all the chiplets could benefit from or could use or could abide to. Um, so I'm thinking that, for example, we would need at our minimum some source and destination fields,
Correct. Yeah, I
right?
mean, you
Yeah,
need source, destination,
yeah,
quality of service,
yeah.
and whatever the payload is, command plus data
Correct. So
command.
if we can define this minimum set of information that we need to send in this packet, and maybe expand on this could be done through UCIe, this could be done through a bunch of wires, look into all the other, I think, packets, standards that are coming out of OCP, and then also look into how would this look like if we had an ideal world where we could have these parallel lines running through the chiplet to chiplet. Um, is this how much overhead are we thinking about? So yeah, think about a little bit about that. I think
Yeah,
and put it in
we
the
can.
paper.
Yeah, we can.
Okay, so I'll write and so I'll let me write my email, or maybe George, do you mind if you write my email in the chat?
Yep,
So and then and
I will.
Anurag, you can also maybe write your email, and then we can. And Arvin, we can invite you also to the conversations. I know you have a lot of expertise in UCI as well, so maybe we can get something really interesting out of this section.
Sure.
Okay, and then so and then we start to think about so we have the chiplet family that we have defined for AI, and then And then what we are going to say is we're going to have what kind of specialized architectures can we build with this? And in this case, I think Arvind is right that we're just looking into something that is very homogeneous to start with, because it's a very big problem we're trying to solve here. But we can define two big different architectures that we could build. So we, in general, what happens is that when you have a systolic array, we build them squared. And then when we build those squared, what happens? Yeah, so when we build those squared, most of the processing elements are wasted, are not used, are idle. So if we can find what is the optimal size of the processing element array of the systolic array that matches the benchmark, that would increase the energy and performance of the system. So we said, okay, so we can have a long array instead of a square array that would target benchmarks such as deep speech. And then, and that would be kind of what we're going to be building around. Or we could have the square array, right? And for the typical squared array. But what is interesting about the squared array is that we could have different sizes of these. So we could have a very small one that would fit something like Sentimental CNN or ResNet 50, that is a 128 by 128. That's what we see in the TPU accelerator, Google's TPU accelerator. But we could also have something like this 256 by 256 that is more ideal for most of the CNN work. But when we look into the transformer, I was at the beginning, I was a little bit confused. I was thinking that if we accelerate the headers of the transformers with smaller units, that would be faster. But the reality is that the majority of the time that it is taking a transformer, the computation of the transformer is on the large matrix multiplications. And
That's
then
correct.
go ahead.
Yeah, that's correct.
Yeah, okay. So that's why instead of going for the headers, we should go for the large matrices, and then that's why a 512 by 512 systolic array would benefit a transformer. So that's kind of where we want to play with. We want to say, okay, we have all these different family of chiplets. Can we build completely different systems to avoid, maybe energy waste, and to make it more performant for these specific benchmarks? And this will help us, of course, build when we start to look into beyond AI. Okay, so those are kind of the different kinds of systems that we could build. And then I try to summarize them here in table 5. So we have we have two big sections. So we have what happened if we're using a sub 20 nanometer system in package, if we build everything in sub 20 nanometers, and what happened if we go to sub 10 or sub 5 nanometers, with sub 5 nanometers being the most advanced technology that I think exists today. And that's work that was done by Boone. So and then what we can do is I try to summarize the different characteristics that we would have for the different ones, for the different architectures. So we have the small, we have the medium, then we have the large, and we have this one I put as the long one. And then here are summarized all the different characteristics of the chiplets, including the interposer size. So I have to complete some of this. I have to complete some of the information, but one of the things I wanted to call attention to is that we're using a sub 20 nanometers and trying to build something for a transformer. The interposer size is going to be 64 by 64 millimeters, which is unfeasible for today technology. So that kind of gives us an idea of what is possible. And it would be nice if we could look into the roadmap and see what is possible today versus what is going to be possible in 5 or 10 years, and evaluate, okay, is this going to ever be possible? Are we is it worth, should we look into
Sorry,
a 60?
why do we say 64 by 64 is not feasible?
I think it is not feasible. This is beyond beyond the 1.5, 3 3 3 times the reticle limit, I think. But I mean, I might be wrong. So what do
No,
you
it is,
think?
Luis, if you look at the recent TSMC announcements, in next 2 years, it will be touching the reticle size of 6.
Okay, but that's in
So,
the
I
next
mean,
2 years, right?
yeah, so this, what you have is roughly reticle size of 5.
Well,
Yes.
I'm sorry, are we talking about a silicon interposer or are we talking about like just something that doesn't require advanced packaging? I mean, I'm not quite sure.
I think that is a good point. So in this case, we are talking about an ideal case where we have an advanced silicon interposer
Okay.
with a bump pitch of 20 micrometers. We have to repeat the experiment for when we're using UCIe and or a bunch of wires, whatever we can do first. But I guess what I'm looking after is maybe we can say, okay, so this might not be possible today, but this could be possible in 2 years or 5 years, according to TSMC roadmap. Would that be?
Well, yeah, I'm trying to be a little careful here because essentially
Yes.
what's happened is up to Hopper, TSMC was using a real silicon interposer.
Mhm.
After Hopper, so like for Blackwell, they are putting local bridges in between chips or chiplets,
Mhm.
whatever you want to call it. And that allows you to scale out significantly more. So I don't think enabling a pure silicon interposer at that size is necessarily the right thing, but one could say that there will be an advanced packaging interposer option available
Yeah,
at that size. And I
that's a
think that's
good,
probably even true
good point.
today.
Yeah.
I mean, I would have to look at the sizings, which would be pretty simple, but we could look at a Blackwell today or a Rubin, which is their next step. And I'm pretty sure that will fall in these sizes.
Means
Available.
Rubin Ultra is 4 reticle dies with 16 HBMs. So you can imagine that is already 6 reticle.
Yeah, exactly. Yeah. So I think that's within
But
shooting.
but
distance, if not, they're okay.
that is slotted to use the CoWoS L or L, which is
L, which
the
is
one which you are
exactly
talking about, Arvind.
exactly L, which is the local interconnect between rather
Correct.
than S, which
Yeah.
is the full silicon.
But they still call it interposer because
They still call it an interposer. It's a name I find very misleading, but it's correctly, yeah, it is still called CoWoS L, but it is
Yeah.
not a pure silicon interposer everywhere.
No, it's not. I mean they use I don't know what material, organic some material to fill
Yeah,
in.
it's
It's unlike
exactly.
Intel's, which embeds into the substrate. This floats above the substrate effectively. You can think of that.
Intel's is just different. Yeah, well, okay. There is a similarity because as you just said, Intel's is a local interconnect as well, and it is embedded in a substrate.
Yeah,
This one is at the surface.
correct. And there are other startups I know who are working on these technologies where they guarantee roughly the organic substrate matching. They can give you 30 to 30 micron to 40 micron. I'm not sure if 20 or when is in their roadmap, but these things are coming up.
I think all of these things are really on the horizon because everybody has this common, challenge.
Okay, I mean I think that's great. Let's do this. Why don't we I don't think I have a section for that, but can we add a section that talks a little bit more about the interposers, the interposer size, and we don't I mean, again, we don't need to do a lot of math work here. All we need to basically write down what we are discussing here, and then include some of the roadmaps for the different companies. Can I give you guys that task, Arvind and Anurag, for you to maybe give like 1 paragraph or 2 paragraphs, and then some links that we could, talk about this horizon for bump pitch and interposer sizes.
And I also put a link in for the HIR chapter. It's written by people from Intel and TSMC, and it's basically a pre-competitive road mapping effort that cuts across the different foundries and assembly houses.
Okay, I'll get it. Okay. And it's 2024. Yeah, it's pretty recent. Okay. Well, the other thing. Okay, so here is showing like the examples of what we could do. So this is a very generic array, AI array, where we have a systolic array, and then we have memory, and then we have control in this corner. And this control is something that we haven't discussed yet, but like, I think the most straightforward way to solve this is having a RISC-V with an ISA extension for making control a little bit, for making this memory and data flow control efficient. But is anyone does anyone have any strong thought about it or feeling about how this control chiplet would look like?
Not yet.
Okay, so I don't know if
There was
Gilbert,
yeah,
go ahead.
there was a presentation recently at the ChipCon by AMD, I believe, on something they called an anchor chiplet. And they go through all of the functions that it should have to control a collection of chiplets. That might be, and I have the presentation, I think. That might be worth at least reviewing.
Oh yes, that would be super helpful. Thank you so much. If you can share that presentation, or the link, we can take it from there.
It depends a bit on whether you want to do your networks as master slave or peer-to-peer. If you're doing kind of peer-to-peer arrangement, then you can have a few potential masters in the chip. The RISC-V processor type things are pretty small. And then if one's broken, you can just pick another.
Yeah, I think that's interesting. So maybe Kevin, can I give you that task? So maybe you can think about how the different kinds of, like, what you just mentioned, master, slave, or how many, how that would look like with a RISC-V. And it doesn't have to be a lot of, it's more like a thought process that we can, maybe have in a paragraph that is coherent. Would that make sense, Kevin?
Sure. Yeah.
Thank
I
you.
mean, there's some stuff with the Open Atomic Ethernet guys where I'm kind of looking at things where stuff that can talk to the network just registers itself, and then you see what you have and you see what it's connected to, like, kind of self-assembled.
That actually sounds way better, because if we can connect this with this work stream that you just mentioned, the atomic, that would be really cool as well. So okay, so I'll write your name for that one, for the control chip. And I don't know, Gilberto, I don't want to put you in the spot, and I don't know if you're listening, but if you have some idea or some thought about this RISC-V control chiplet, that would also be appreciated, if you have some input about that.
So Lisa, if you can send me the paper, I'll have a read through the paper. I haven't been joining this forum for a while, so I was trying to reconnect. So yeah, happy to have a look and see if I can help.
Okay, so so then I'll send you the paper. Do you mind if you write your email in the chat so I can get it? And then and then what I was gonna say is, and maybe Gilberto and Kevin can maybe get in touch and look into it, but yeah. And then the other thing, what is here from here? I'm trying to think what else. Okay, yeah. So this would be like, this figure A would be the generic architecture, but then figures B, C, and D show kind of the different configurations we can have. And then if we get our way, this could, this systolic array could be replaced by, for example, the stencil accelerator that George was talking about, or the HP accelerator that that George was also working on. So let's, like this would be the starting point. So this is the small array. C is the small array, the smallest possibility that we could have, that it would resemble the the simplest AI accelerator that we could have today. And then this would be I have a mistake here, but this would be this would also be a small array, but with a smaller chiplet, where we mix, for example, two technologies, where we mix a sub 20 nanometers technology, where we only can fit 64 by 64, with a sub 10 nanometer technology to leverage the higher density of memory. I don't know if anyone has some strong feeling about this architecture D, or if anyone thinks it's not a good idea, or is, yeah.
Are you looking at 3D stacking at all?
Yes and no. So not here, but we do have a section for that. If I don't know if you want to take a look at that, Kevin, also as well. But
Mhm.
we talk about 3D SRAM integration, and I think what is interesting about talking about 3D SRAM integration is the fact that SRAM is not going to be on top of the logic, so we don't necessarily have to worry that much. I'm not saying it's not a problem, but we don't have to worry that much about thermal dissipation if we argue that basically we will have a stacks of SRAM.
Mhm. SRAM's not as sensitive to heat as DRAM.
So we could argue, so we do have some arguments here on what happens if we do, these are very weak arguments at this point, but if someone is interested on adding up on this 3D SRAM argument, and then think how, the requirements. For example, one of the things that I'm struggling with, and I don't know if others have thought about it, is the interface that we would use for a memory chiplet that we meant to have 3D integrated. Would the interface would the same, or would look like the same if we, can we reuse the chiplet for 2D, 2.5D integration and 3D integration, or those two would be completely different chiplets?
You'd
And that
probably
is
sacrifice some area for bigger TSV type connections, but you
for
can make the chiplet work both ways.
okay. Okay, so yeah, so that's one of the things that maybe we can talk about, the compatibility, especially because we are a modularity work stream. So what we want to do is can we reuse the chiplets to build completely different architectures? And
I used to work with a company that did gate arrays, and you would do the last layer of wiring as a separate step. So you do chiplets that don't have everything wired, and then the last thing you do is, because you don't need to do that in like a proper fab. You can do something like inch fab or something like that and do a last level of wiring.
Okay. That's interesting, and that's actually that would be nice if we could have like a discussion in the paper. What else do we have here? Yes, these are some latency and energy results. Latency and energy results. I'm not gonna go into them because I do need to run a little bit more simulations to make them to fix them, to fix some numbers that I don't think that I have some problems. But we can talk about them later in the next meeting where I fix the problems here. But so to finish here, there are other things that we need to talk about that we don't necessarily need to solve here, but we need to discuss like what does it mean for the I/O chiplet, and the reason why the I/O chiplet is important, because when we want to scale up, like this is a single system in package, but when we think about HPC, and when we think about more like complex systems, we need to scale up. We need to be able to connect these chiplets in a rack or in several racks. So we need to understand, maybe have some idea of what this I/O chiplet would look like. And that's something that I haven't looked into. So if anyone has some strong ideas or feelings, or is passionate about this, I would appreciate help here. Or maybe if you can contact with the right person to do this, that would also help a lot. I don't know if anyone has some ideas or expertise in this area in how this IO chiplet would look like.
So, in terms of, do you expect this to be like a, I mean, I haven't been following this discussion for a bit, but that IO chiplet can be used to connect to external memory. I am guessing that's one of the options, or is this supposed to be connecting to something like a sensor?
So I think that's the considerations that we will have to make, and like in this section, right now what we have is we have two chiplets, one for memory, one for accessing the memory, one for accessing the IO. And IO would be for chip-to-chip communication, chip-to-host communication, or chip-to-sensor communication in the case of, for example, if we have a small array or a large array, depending on the type of sensor. If it is an HPC sensor, probably it's a large. But this is up for debate. Like if for example, someone thinks that we could merge the IO and the memory controller chiplet into one, that's also something that we could talk about. The reason why they are separated is because maybe what we can think of is there is this application that where we could, we have 3D stacks, we could fit all the parameters in this RAM in memory, and when we wouldn't need a memory controller, versus there is this other application where we do actually need to access the RAM and we do need memory controller. So I guess when we separate IO and memory, then we might have this flexibility here. I don't know if that makes sense, Gilberto.
No, it does. I guess in that context, you could just assume that this IO could be a PCI Express or something like that, or Ethernet connection, I guess, in the simplest way.
Yeah, okay.
So having it separated as you have it is an option. I don't see anything wrong with that. In that case, the IO obviously is not the memory controller as you described. It could be.
So the
go ahead.
purpose, sorry.
Go ahead, Arvin, sorry.
Sorry, I didn't mean to cut you off. I just I thought you were finished. The purpose of the IO chiplet is to go off this package. So you've got a collection of chiplets on some package, and you have another. You want to go off package to another collection of chiplets or to another chip. So it has to have like a PCIe driver, as you were saying. And this type of chip is there. If you just look at a roadmap, or if you go on to, for example, AlphaWave's website. AlphaWave is a company that makes these. Now they were recently, there's an acquisition, I think, that was announced, so I won't go into that, but this is one of their key chips, and I think if you can find this information quite publicly, that has a UCIe interface on one side and it has a PCIe driver on the other side. Now it would not really extend over your 6 chiplets like the way you've shown it here, or 5 chiplets. It would just have a single entry point and then a PCIe. So you would just stick this off one of these chiplets. There are other examples. For example, Dream Big Semi is another company that has multiple ports. You attach multiple accelerator chips and then you put a big hub down. And that hub it's a little more like a Swiss Army knife approach. That hub enables you to do a memory connection. So it could actually serve as your memory controller. It also would enable you to do like a PCIe type connection, but it's a much bigger chip. So I think there are examples of this in the industry that we could cite.
Yeah, I was just going to mention the AlphaWave Semi. It has PCIe, CXL, and 1.6 terabit Ethernet.
Ethernet,
yeah,
exactly.
And you can flexibly switch between lanes that speak either of those 3 protocols and chop up the bandwidth different ways. But it's a great example of an IO external, get off the chip IO chiplet. And I think if we have multiple examples, so the Dream Big I know less about, that would be, you could point to those examples and say, this is where industry is going with this kind of chiplet. They already exist. And so we would do something similar, something like that. So we don't look like we're pitching one product.
Yeah.
Okay, yeah, that makes sense. Yes. Okay. Yes. So I'll get the link, and then we can work. I'll send some assignments to see how can we fill up that IO chiplet section. But basically, what we want to argue is that this is completely scalable. So we can have chip-to-chip communication. Therefore, we can have larger models as we, connect several chiplets, several of these system in package together. So I'm trying to remember. I don't want to. I just wanted to write something more. Okay. Yes, I wrote it. Okay, so then we have the DRAM integration, and then basically we have this, right now the way we have it is DRAM is off chip, but we could also have DRAM in package. I guess, I don't know if we need to discuss this DRAM in package for this white paper. We can, leave that conversation for the next one. I don't know, how do you guys feel? It's getting, we have enough material for one white paper, and we can have like the second iteration. So I don't know, what do you guys feel about DRAM in package, DRAM in package versus DRAM off package for this particular white paper?
I'm a little confused. Like when you say DRAM in package, you have memory chiplets, right?
Yeah,
So
yes.
is it a question of whether those memory chiplets are SRAM or DRAM, or?
No, yeah. I think we need to have, like in the system, we need to have a combination of SRAM and DRAM, depending on the application, right? So some applications won't need DRAM, some applications will need DRAM. So the argument I'm trying to see is we could have a system where we have, of course, we have SRAM, but we could also have DRAM. And yeah, in that case, we could have less SRAM, more DRAM.
Well, any reasonably sized AI application today will really need DRAM. I mean, just because the model sizes and.
Yeah, so, but I guess the argument is, do we have it off chip, sort of off package, or we have it in package?
Oh, in all the HBM stuff's in package, so the precedent is well established.
Yeah, I was gonna say I did look into some HBM stacking based on some feedback, like from a couple meetings ago. I can show that maybe at the next meeting, along with some RTL synthesis results, if it makes sense.
Okay, so I guess the consensus is we do have to care about in package DRAM for this work. Okay, so George, I'm gonna put you on the hook, so you can show your results, and maybe you could take care of some of that section.
Yeah, sure.
I guess
You can.
my worry is how big the interposer will look like with that. But yeah.
Yeah, you can use the standard form factor of the HBMs. They've remained the same for a long time.
Right. And I think one of the things we talked about is 3D stacking of HBM over, and that's sort of what I found information on. But I don't like that's more out there in terms of technology readiness. So we don't have to use that. But in any case, I was sort of I was thinking of answering that question in terms of, okay, how much memory capacity and how much memory bandwidth our accelerators are going to need. And that will tell you where the memory should go, along with the projected latency together and the impact to the application. Because if we can avoid having some memory on the interposer, then we can have more compute. If that makes sense.
Well, yeah, I guess, what is interesting, sorry, someone was going to say something.
Yeah, sorry, I was just going to say it really depends on the workload, because if you look at Gen AI workloads today, just piling on more and more compute is not really going to help you. It's all memory, driven essentially.
Yeah, okay, that makes sense.
You want the right ratio between
You want the right
compute and
ratio,
memory.
yeah,
Yeah.
exactly. And
Yeah.
it was for a long time very compute dominated, but now with KV cache and a lot of these other,
Well, you don't really want to cache things if you don't have to. I mean, you want to.
I think cache is a misnomer, but it's called KV cache. So I'm not talking about caching things as much as I'm kind of talking about having local storage close to the processing elements, and a lot of it.
I think I posted something last week on the efficient computer E1 processor. They're claiming like 100 times less power, basically by doing in memory, not moving data around.
Yeah, the in-memory is another technology innovations going on. There are a bunch of startups putting money into it.
It's one of those things, if you never miss cache, then you don't need branch predictors, you don't need cache coherency, there's a bunch of things you don't need.
Yeah, I mean, it's all about moving the data, right? If you don't need to move it, there is no picojoule cost.
Yeah.
Or the least of it.
People kind of forget that the computer architectures we have at the moment are sort of very old and used to having to swap things in and out to like magnetic disk. So, they're not really an architecture designed for something where you can die stack the memory right on top of the processor.
Yeah, those are coming too. You can see even NVIDIA's published talks in last 2 years. They're talking about all the 3D stacked memories on top of GPU. So it's not too far.
I think there are many avenues we could take with this. There is the stacked HBM on logic, which is now becoming an HBM4 standard. There are several companies which are just announcing a single layer of DRAM on top of a processor, more like what's called a last level cache. Again, it's not necessarily a cache, but that's what it seems to be called. And and then I think there's the chipletized idea that you're showing here, which might be a way of a smaller form factor DRAM than an HBM. And that also allows you to kind of tunnel through from one, through a memory chiplet, because, an issue with an HBM is that it kind of defines the boundary. You can't really go anywhere
it's
after
not a
the
good
HBM.
idea, HBM. I mean, when you think about it, an HBM is a stack of memory where you're creating a 3D volume for your data.
Yeah.
That only has a surface for access. And in some cases, you're down to an edge. So it's really,
Exactly.
it really becomes a
That's a
bottleneck.
That's a key problem. And the kinds of architectures you might be proposing, it would be nice if you don't really have that restriction.
Yeah.
So
I mean, the
think
thing
there
I
are at
think,
least there are many avenues we could take with this, and I think we have to decide what do we consider really in scope here.
yeah, but I mean, if you do something like a Control-Shift-Escape on your Windows PC and actually look at how much memory any process takes, lots of them are quite small. So you can break them out and do them separately with their own memory fairly easily.
So we have 2 more minutes. So what I would propose is let's start next meeting with the memory discussion. With George. George has some information, so he can start the discussion with what he found about HBM, and then we can keep refining the idea so we can decide. We don't have to decide anything, actually. We can actually lay down all the different options that we could have to build this in package DRAM. Okay, well, thank you so much for the discussion. I have some notes. I'll follow up with some emails and assignments. I'll create a table and then we can start populating the sections that we're missing. Thank you so much, everyone. Bye-bye.
Bye.
Thank you.
Right. Thanks.